Good morning, everyone, and welcome to the first webinar for the Geo Week Open House. Today, we are pleased to welcome Tory Smith, Product Manager from Mapbox. Tory, would you like to turn on your video and mic? He will speak about the new Mapbox Product Vision SDK that's been beta for 1 year. Over to Tory, please.
Hello, everyone. Is my microphone audible for everyone? Right. Let me go ahead and grab control here and get started. Okay, so thanks again. It's really exciting to be here and joining everyone. I'm calling in today from San Francisco, California in the United States. Today I'm going to be talking about the Vision SDK, which we refer to as an AI Copilot for the road. So I'll dive into that in just a few minutes. First, I'm going to talk a little bit just about my background. Let me minimize this so the screen is easier to see. All right, so just a quick intro to myself. Again, my name's Tory. I've been at Mapbox for about 2.5 years now. My background is a combination of sort of engineering and product roles. And my passions really are maps, mobility, and machine learning. I got my undergraduate education at Virginia Tech over on the East Coast of the United States before coming out to California about a decade ago and got a master's degree actually in mechanical engineering at UC Berkeley. And most of my career prior to Mapbox, I actually spent working on autonomous vehicles. So this picture here on the right is actually before we set off on a cross-country autonomous drive from San Francisco, which is in this picture, to New York City. In an autonomous vehicle back when I was working at Delphi, which is now Aptiv. Since then, spent a little bit of time at Ford Motor Company working on autonomous vehicle efforts there, as well as Drive AI, which is a startup also based out here in California working on autonomous vehicles, before finally joining Mapbox in early 2018, where I've been spending most of my time working on the Vision SDK, which will be the topic of today's presentation. So a little bit of background on Mapbox, in case you're not familiar with us. We refer to ourselves as the live location platform. So I'll talk a lot in this presentation about the importance of data and the importance of the freshness of that data, which is a really important dimension in terms of what makes data really valuable. So what's exciting about Mapbox is we don't have an app that you can use like in the App Store or download or anything like that. Rather, we have SDKs, APIs, and live data that we use to power other applications. So our customers are developers. So today we have over 2 million registered developers that use the Mapbox products across maps, search, navigation, and data services. Our APIs and SDKs and data power over 600 million users every single month. And devices, people, vehicles travel over 350 million miles per day. And the anonymized data that we're able to collect from all that motion allows us to build products that give us more insights into how people move through the world. So that's very exciting in terms of what we're able to do just with anonymized GPS data. But obviously, there's also a lot of really interesting things we can do with camera data that comes from vehicles traveling through the road networks across the world. A couple examples of where you can see Mapbox in the wild today. We're used a lot for data visualization from customers like Tableau. We work with DJI for drone navigation. We work with Facebook for powering Facebook Local and their maps. Snapchat is one of our largest customers. Also work a lot with the weather company. Anytime that you need to understand where you are, so you look up the weather for your specific city or zip code. And then finally, Yahoo Japan is one of our more recent customers that we're working with in Asia. So getting into the real interesting pieces, like maps, something I have a real passion for. And one thing that's really interesting about Mapbox is there's not a single map, but rather any map that you look at is actually something that consists of over 100 different layers of data. So everything from satellite and aerial imagery to the base map, which is things like water and land use, to terrain, which includes information about terrain types as well as elevation, Obviously, the road network is a very important piece, but then we have things like points of interest, addresses, traffic signs, and then what I'll be focusing a lot today is actually the real-time aspect of that data. But anytime you look at a map, it's usually grabbing a few different layers from this list. Seldom would you use like all 140 of them, but it really depends a lot in the application. And that's really why there's so much versatility in terms of what you're able to do with a map based on the types of information that are going to be important for those who are using that map. So again, focusing on the live aspect, what do we mean by live data? So if we start with just the basics from what anyone who's ever opened up a Maps application on a mobile device before, you sort of start with a point, that is you, the blue dot or the green dot. And that piece of information, when that is registered, it's essentially just a time, an instant in time where you are, a latitude and longitude and elevation, and then maybe some notion of how accurate that piece of information is. And the accuracy of that information depends on how good the satellite signal is, as well as a lot of other factors. But what starts to get interesting is once you know where you are, then suddenly you understand where you are in relation to other objects that are around you based on your location inside of that map. And then once you start to move, we start to get a lot more of an understanding of things like traffic in terms of how multiple people are moving through the environment. And from there, we can begin to draw inferences that make it easier for folks to get around, to understand where they need to be and how quickly they can get there. So well, I'll show a couple examples of how that information starts to get really interesting at scale. So this is actually a raw image of anonymized telemetry data in San Francisco near where I am right now. And what you're seeing here is it's quite noisy. So you can sort of make out what the road network looks like, but there's a lot of noise involved. So a lot of the secret sauce around how we operate to turn all this information into data that's really useful comes from filtering. So if you're standing right at the X, if you gathered maybe 100 or 200 points, they're going to fall all over the place, but most of them are going to fall within 10 meters. And if you actually take an arithmetic mean of all that data, the average is going to be very close to exactly where you are. So using that piece of information, the distribution might look something like this. So using all that information, we can take a picture like this and turn it into a picture like this, where we've done a lot of filtering. We can reject a lot of instances where a single trace might have taken a single device, like traveled like half a mile in a second. We know that most people don't travel like that. So through a lot of filtering, we can get a much better understanding of how people are moving. And if you look close, you can even see examples of difference where lots of vehicles travel versus where a lot of pedestrians are walking through squares. Some of the spaces where you see less straight lines, that's actually down City Hall in a park right here in the center of my screen. So another example of that is once you conflate motion rather than just location, there's also a lot of interesting information that can jump out of the page at you. So in this example, we've actually filtered the probe points that we collect by velocity. So the brighter greens and yellows are faster moving, and the darker orange colors and reds are slower moving objects. So what you can make out from here is you can actually start to see the different lanes that are on the freeway. And then the very bright lanes all the way to the left in the middle of the page are actually the high occupancy vehicle lanes, which are much faster. Whereas down here on the frontage road at the very bottom are lots of parked vehicles or vehicles that are driving very slowly, because you can see parking spaces and driveways down there. This is actually an example of where collecting lots of that data over time also allows us to understand even how many lanes are on a given road once we have enough data. This is another example showing how we can actually discern the direction of traffic, and we've adjusted the brightness of these probe points by the acceleration and deceleration profiles. This is an example of coming in and out of an airport, and you can actually discern profiles of which of these traces originated at the airport and which of these traces originated outside of the airport to figure out, and you can actually visualize with live data where folks are circling the parking lot to find parking spaces versus folks that are leaving the parking lot and just driving in a straight line and getting back onto one of the arterial roads that take them in and out of the airport. Last example I'll show of just working with basic probe data is if we look at a lot of traces in a dense neighborhood area like this, we can actually discern just from anonymized probe data how people are traveling through neighborhoods to figure out things like turn restrictions. So which streets are folks allowed to make left and right turns versus where are they only allowed to go straight. So just an important side note here to mention about privacy. This is something that's becoming more and more important in our world, and something that we programmed in from the very start to protect the privacy of our users. So what we actually do is we take the individual location data points on our server, and we break those into chunks. And then at the beginning and the end of every trip, we throw out that beginning and that end, which makes it impossible for anyone to figure out exactly where you started from or exactly where you ended. And what that does is protects anyone from, even if they had access to the data, for being able to figure out where you work, where you live, or anything like that. So that piece of privacy protection is something that allows us to operate in full compliance with industry best practices and standards and things like GDPR, if that's something you're interested in. So finally getting into the visual piece of this in terms of what happens when we add visual context to location. So I was talking a lot about the importance of understanding how movement happens at a large scale, but if you, instead of just having probe points, actually have images of the road at all of these places, there's a lot of really powerful things that you can do. So a lot of my background comes from working with autonomous vehicles, where you have a very low number of sensors that have very high fidelity data coming through, and it's very expensive to process all of that data, and obviously expensive to maintain a fleet of vehicles like this that have any kind of strong coverage. So what you end up with is actually sort of a table that looks like this. So in terms, if your axes are richness and then the coverage of that data, if you look all the way to the left and all the way to the top, you have things like LiDAR point clouds, where you have extremely precise 3D beautiful maps that maybe have centimeter level precision, but those are very expensive to make. And we have only very small amount of the world is mapped in 3D with that level of precision. And at the other end of the spectrum, we have GPS probes, which any mobile device on the world, as well as billions and billions of other devices, have GPS signals, and anonymizing and collecting that probe data is what allows you to always be able to open up your phone and at least get an estimate of how long it's going to take you to get from point A to point B. So that data is immense in terms of the volume, but not very precise. It's not very easy to build a three-dimensional map of the world just with GPS probes. So really the question here is how, and sorry, one other piece here. So oftentimes we associate things like point clouds with level 4 driving, and we associate things like probe data and lower definition maps with maybe level 2 driving or adaptive cruise control and things like that. But what the real question is, how do we get great richness and great coverage and do this in a way that's economical? So the Vision SDK is the product that I work on at Mapbox. It is actually something that we are really excited about in terms of starting to make that dream into a reality. So what I'm showing here on this slide, apologies if the videos are kind of choppy because there's quite a lot of information on the screen right now. What I'm showing here is some of the ways in which we're bringing that to life. So you can think of the Vision SDK as a tool. It's an SDK that runs on iOS, Android, or Linux. It can be input into basically any application that is designed to run in a camera that is moving through the road network. So that could be a car, it could be a bicycle, a truck delivering a package. Any moving along a road application is something that is really interesting for us. So we can do things like augmented reality navigation, which is what we're showing on the left side here, and the top left and the bottom left actually, which is something that works all over the world already. The bottom right is actually another example of augmented reality navigation, but a way that we're actually taking points of interest from a two-dimensional map. So any point that has latitude and longitude associated with it is really easy to drop onto the map and actually render in 3 dimensions. And then finding the top to understand things like lane geometries, vehicles, pedestrians, as well as read and understand signs. So all of this together is quite powerful, and we've designed it to be very lightweight. And by lightweight, I mean it is dense enough and computationally efficient enough to run on devices that pretty much every driver on the road today has. So any mobile device, pretty much, any connected camera with a modicum of compute is able to run this technology, which is really exciting and makes it accessible to billions of people on Earth. So in terms of what we do with the Vision SDK sort of under the hood, so these underlying computer vision technologies that make all this possible, we do classification of signs. We do semantic segmentation, which is actually understanding the shape of the driving environment. And we do object detection, which is actually understanding the location and classification of discrete objects and understanding where they are relative to the camera. Remembering these 3 things is actually quite easy because they also form a very technical haiku. So all three of those running together. So I mentioned detection, which is understanding, that's where you see sort of these bounding boxes. You understand where all these objects are, what they are, and how they relate to the camera. We understand segmentation, which is the shape of the roadway. And then we do classification, which is when we see things that we want to very specifically classify, like road signs, for example, we're able to read those signs and then make that information available. And that's particularly important and valuable for applications where you might want to be able to tell the driver what the most recent speed limit is, or warn them that there's no U-turn allowed, or that there is a no parking sign nearby. That technology is quite valuable, and today we have coverage for speed limit signs in most of the roads in the world. So all over the United States, the European Union, China, Japan, as well as other geographies. In terms of how our system architecture works, one of the things that we're really seeking to accomplish with the Vision SDK is to make it very accessible and also very modular. So we have the core that runs all these neural networks, all the machine learning I was just talking about, and then we actually expose all of the raw information that comes out of that. So the segmentation, the detection, the classification, and then we have modules that you can plug in to do things like augmented reality, which is AR here, driver assistance, or ADAS, which is this middle module. And then one more recent thing that we're adding currently is events. So basically the ability for a developer to utilize an if this, then that framework that's all based on where you are and what you're seeing. And making all that information available to the camera has some really exciting applications. So just to give a few examples of that, one of our first customers that applied this in a driving application is a company called Sogu based in China. They have about 300 million monthly active users. They use the Vision SDK to build an augmented reality navigation application that plugs into their driver navigation app here that they released for both iOS and Android. This is actually an example of a demonstration we showed an embedded vehicle system with Samsung and Harman at CES 2020. At the beginning of this year, where we actually used Mapbox to build this map that you see in the center, but also in this pseudo heads-up display, turn-by-turn directions that are illuminated with an augmented reality guidance system, which you're seeing on that wide and thin display right there. Another cool thing that we're able to do with our augmented reality navigation is actually understand the depth of the environment to do things like occlusion, which is what we're showing here. So essentially, instead of just drawing objects in the environment, we're actually also able to understand in real time the geography and the depth of every single pixel on the screen. So if I pause this for just a second, you can see that we're dynamically adjusting the opacity of these chevrons here based on where other objects are. That way, if you're creating an augmented reality navigation system, you're never drawing guidance that covers up something that is important to the driver. Another example of where this is really exciting, both for embedded vehicle systems as well as aftermarket devices for things like safety, is this new system that we've developed with our partners Raven that actually uses the Vision SDK onboard their dash camera to detect unsafe driving behaviors, as well as warn drivers about road hazards, such as a pedestrian or a cyclist that's in the road, as well as to warn about things like tailgating and warn about things like changing speed limits. And finally, what I wanted to touch on is tying all of this real-time understanding of what's happening in front of the camera back into the live location platform. So when I say adding location context to computer vision, that takes us to what I'll show briefly here. So on the left, this is just a video of driving down the road in San Francisco. We're running the Vision SDK, so you can see here we've actually drawn a grid, which is our understanding of the depth of different objects in the scene based on where we've detected the horizon and the vanishing point to be. So for every object we see in the environment, we have a good idea where we are from GPS, and we have a good idea of the relation of the objects that we are seeing relative to us using computer vision. And that means that every time we drive by an object, such as this 25-mile-per-hour speed limit sign that's recently changed, we can detect that piece of information without having to send a picture of it, because we're able to detect it in the moment. The reason that's really powerful is typically you would have to either record all this information and study it in post, or you would have to have a very powerful computer in the vehicle, or you would have to stream the video to a server in another location, which is very expensive in terms of data utilization. So what we were actually able to do here is take this piece of information, which is just the identification of a speed limit sign, its location, and that time, and transmit that with only 72 bytes of data. So it's very, very cheap in terms of data. So instead of just a probe point, we actually have a probe point and associated metadata that can tell us pieces of information such as a changed speed limit or a closed lane, or if there's been an accident or an emergency, to know exactly where that is. That's a very powerful piece of technology that has a ton of applications for live mapping, for logistics and fleets, as well as for the automotive industry. And this is something we're really excited about giving our developers the opportunity to incorporate this functionality into a lot of new and exciting applications. So what this starts to look like at scale, if you're only interested in like changes in road signs or parking, for example, just a couple vehicles driving around, I believe this is Denver in Colorado in the United States, just a couple of vehicles driving around for an afternoon, we're able to grab all of this information. And this is all parking, locations of stop signs, do not enter signs, speed limit signs, pedestrian crossings. So you can imagine how this starts to become really powerful, not only for building maps, but also for keeping those maps up to date. And the ubiquity of having so many different connected cameras in the world. So already today, billions and billions of connected cameras that can run our technology out of the box makes this a very powerful technology with potential for very rapid adoption, which is something we're really excited about. And then the last thing I wanted to show is actually combining not only static data, but dynamic data. So what we've done here is just created a short demonstration of connecting the Vision SDK to a fleet management system. And instead of looking for specific features in the environment, like a sign, we can also detect unsafe driving events. So this is something that some of our fleet and logistics customers are using. In this particular example, it can automatically detect if a driver runs a stop sign and then note the time and the place, and even automatically capture a short video clip of that for coaching purposes, for insurance and auditing purposes, as well as driver exoneration in many cases, which is especially important in the United States, where one of the largest, or if not the largest, controllable costs for a lot of fleet drivers in the United States actually have to do with insurance, accidents, and injuries that happen on the job. So this is sort of a quick look into the future, but something that's going to be a reality very soon. So final piece, one exciting thing always is this is something that's very easy to pick up and start using right away. So the Vision SDK for iOS as well as Android is actually free to download, install, and start using on our website, mapbox.com/vision. And with that, I think I'll jump over and try to answer any questions that I can.
Thank you very much, Tory, for the very interesting presentation, demo, as well as a nice haiku. I shall also invite my colleague Asa to join me to take questions. Please place your questions in the Q&A box. Asa,
Tory,
do you have the first question for Tory?
Yeah, Tory, I have a question.
Sure.
What kind of devices are supported for using this Vision SDK? I mean, what do we use certain type of cameras or?
Yeah, that's a great question. I usually dive into those questions if I have a little more time. But the short answer is on the iOS side, we support any iPhone made in the last 4 or 5 years, so going all the way back to the 6S. On the Android side, we support pretty much anything with an ARM-based processor that is from the past couple years. So in terms of total numbers of devices supported, there's a more complete list on our website. But right now, I can say confidently that there are billions of devices that almost anyone, if you own a mobile device, would be able to run the Vision SDK, which is something that we're focused on. There are not a lot of restrictions on what types of cameras that we support. I will say that we have not yet found a camera that we cannot work with.
Thanks.
Mm-hmm.
Let us see whether we have any other questions. Okay, if not, maybe I'll answer. I'll ask a couple more questions.
Okay.
Will this work for, say, sidewalks?
Good question. Yeah, that's something we get asked. Yeah, that's something we get asked about a decent amount. So if you're familiar with Google actually has a really interesting augmented reality navigation system that is designed for pedestrians to use. The way that system works is the camera actually compares what it's pointed to with Google's library of street level imagery data, and it's actually sending a bunch of images back and forth in order to be able to do that. That requires a lot more data transmission. So what we're focused on doing is, instead of needing to send lots of data back and forth, you utilize a lot of the assumptions that we can make around knowing that you're traveling along a road. So it's designed to be used for traveling along roads, but even if you're on the sidewalk, if you point it toward the road, it would still be able to tell you information about vehicles, pedestrians, and cyclists and things like that. But most of the features around augmented reality navigation and safety, for example, are associated with vehicles.
So we have a question from Jen Lin. Is there a free or trial version of the Vision SDK?
Yes. So if you go to mapbox.com/vision, you can download the Vision SDK on iOS or Android, and it's free for up to 50 devices, actually. And if you have any questions specifically about device support or how to get started, please feel free to contact me directly. I'm just Tory at mapbox.com.
Question from Gopal: Is Vision SDK supported on WinCE devices?
Currently, we do not support WinCE. We do support Ubuntu Linux for both 64-bit as well as like ARM64 as well as 32-bit Linux. But right now, we're focused on embedded devices, which are primarily in a Linux environment.
It's a question from Dominic. Does it work with ROS?
So we do have some customers right now that are experimenting with implementing the Vision SDK as part of a ROS system. Unfortunately, I'm not an expert, but if you shoot me an email, I can try to give you a more specific answer on that one. I know we don't have any live applications right now that use ROS.
So if a customer would like to work with you from Asia, does Mapbox have a support team based in around the Asian region, or is it right now out of the US?
So I believe we support the Vision SDK anywhere in the world except for Iran and North Korea. So we do have customers in China. We have a lot of customers in Japan as well. And we have support teams in China and Japan and Singapore, actually. So I do not know of any geographic constraints that should prevent us from getting started and building something together. So I would seriously invite anyone here to contact me directly, and we can take it from there.
Great. It'd be great to see if we can actually organize some developer workshops with Mapbox if Joe works in the future, so we can have like a webinar style sessions.
Absolutely. Yeah, one other plug I'd like to give. We do have pretty substantial tutorials and documentation for all Mapbox products that are designed for people to just pick up and start working right away. And almost always you can just do all of this without having to even put in credit card information. You just sort of pick it up and get started. You just need an account. But if you have specific questions, I'm definitely happy to answer those.
Asa, do you have a question for Tory?
Yeah, just another question. With all the video footages that are being harnessed, where are all the images being processed? Does a customer require some kind of a cloud storage or a service, or is this provided by Mapbox?
That's a great question. So for the standard Vision SDK, which is what I've been talking about in this presentation, there is no requirement to store any data at all or save any data, because all the processing happens on the device. For applications where we have customers that want to save certain kinds of data, we have configured a separate interface that allows you to define an endpoint where all that data is sent. But Mapbox does not require you to save any data or store any data in order for the Vision SDK to work.
And in terms of the semantics that's been picked up, who owns all these assets eventually?
When you say assets, you mean who who owns the IP for the neural networks?
No, let's say if the Vision SDK picks up all the road signs, and all these road signs have been geotagged. So all these assets, or I would say layers, who owns them eventually?
Oh, I see. Got it. Yeah. So what's currently happening is we've used the Vision SDK to run on a lot of archival imagery that we have at Mapbox that we've purchased over the years, and then devices that are out driving around. The same way that we use anonymized data to give traffic information, we also use anonymized imagery coming back from Vision SDK devices to update our maps with information like the number of lanes and speed limits, for example. So we actually expose, that data is exposed back into the Mapbox map that then any of our developers can utilize.
Right.
I have one last question from Tom Young. Any limitation on recognizing Asia character signboards?
Oh, yeah. So currently, just to clarify how our sign recognition works, we do recognize a couple hundred different signs, both in Japan as well as China, Singapore, and several other Asian countries. The way our character recognition works is we don't actually do OCR, or optical character recognition. We actually learn to recognize the whole sign. OCR is something that we could do offline, but currently is too computationally expensive to run in a lightweight application given the real-time operation constraints that we have with the Vision SDK. But that's a very good question.
All right, that wraps up our session for today. Thanks very much, Tory, for joining us. And everyone else, do feel free to join us for our other developer workshops for today. See you soon.
Awesome. Thank you all very much.